Thank you very much for having me here. My name is Elizabeth Evans. I work at the University of Manchester, hence all the purple and the branding. Sorry, it's a legal obligation for me. So hi, hello. I've been working at the University of Manchester for over 18 months now in our X-ray tomography lab, but my journey into X-ray tomography started way before then. I've been working using the technique since, oh dear. Actually, I don't want to admit that. No, it's been a while. I've been using it since my master's, where I first analysed geological samples, but I'm more than just a geologist now. I scan all sorts of things for all sorts of people, and I hope to share some of the wonders that can be revealed through X-ray tomography with you tonight. Question, is something like this familiar to you? So just to give you a clue, this on the left is a medical CAT scanner. So find them, they're ubiquitous in hospitals. You lie down, they take a series of X-rays all the way around you, and after some computer wizardry, you get a 3D X-ray of the human body, and the doctors can diagnose what's wrong with you with any luck. And this is actually the basic principle of X-ray tomography. So if you've ever had a CAT scan, or if you know anybody who has ever had a CAT scan, this is exactly the process that you went through. It's non-destructive, which is excellent because you want to be able to see inside the human body without damaging it. And it's also excellent for seeing inside other things as a result. So the story of X-ray tomography is a story of two things. The first one is obviously X-rays. So we're dealing with the X-rays that sit within the hard X-ray zone. So that's the sort of X-rays that you get used for medical purposes, airport scanners, and as they get more and more energetic, you then move into the gamma ray part of the electromagnetic spectrum, but we'll leave that for now. Of course, X-rays are ionizing radiation. They can cause damage to human tissue. So actually, when it is used in a medical context, it is tried to use sparingly. You're only given a CAT scan if that is a diagnostic technique that will reveal something about your condition. They don't go around giving it out willy-nilly. But here's the man himself who discovered X-rays, Wilhelm Röntgen. He received first Nobel Prize in physics in 1901 for his discovery, which we're all very grateful for. This is the first ever X-ray picture. You'll forgive me that the way I tell stories about science is by telling stories, and the story behind it is I find particularly fascinating. So this is actually not Wilhelm's hand, it is his wife's hand. And when he developed the photograph and showed his wife, she declared, in German, obviously, I have seen my death. She was absolutely astounded. No one had ever seen their own skeleton before, and it freaked her out so much that she refused ever to set foot in his laboratory again. I sympathise. No one had ever seen their own bones before, or at least their own living bones before. I'm sure maybe some morbid people had perhaps had an amputation and had seen their bones, but no one had ever seen their living bones before. So there's a couple of versions of this picture, but this is the more famous one that's in a particular archive, and I happen to like it. It's one of my favourite photographs. I don't know what that says about me, but that's the X-ray bit. What about the computed tomography bit? So we're all familiar with computers. So that's the computed bit. But tomography, what's that weird word? So like most things in science, it comes from the Greek. Tomo meaning slice, graphy meaning describe. So it is literally describing something by cutting it into slices. So very nice. And although the maths behind tomography was actually developed pretty soon after Röntgen had discovered X-rays, we didn't really have the computing power until the 70s, where it was finally developed into a working system by these two gentlemen. So Godfrey Hounsfield, who was a British gentleman, and Alan Cormack, who was a South African. Cormack often gets forgotten, but they did actually share the Nobel Prize together in 1979 for their development of computed-assisted tomography. And so I always try and make sure that I credit both men because Alan often gets missed out, and that's a crying shame because a lot of the mathematics is actually based on his work, and Hounsfield mainly did a lot of the electrical engineering. So it really was a joint effort that we now have the technique, not just one or the other. So again, back to our medical CT scanner. Medical CT scanners are arranged in the geometry that they are. So you lie down, as you can see with this diagram on the right. You lie down on a rather uncomfortable looking pallet, and the X-ray source and the camera, the detector, moves around the individual in sequence and takes a series of images. The reason why it does it that way, why it moves around the X-ray source instead of moves around the person, is it's easier to keep a person lying stock still for a while than try and get a person to slowly rotate incrementally around, because the whole key principle of X-ray tomography is that you must be able to take a series of X-rays all the way around the object you wish to image. Now, in a lab, such as the lab that I work in, we are luckily not dealing with the human body. We're dealing with often very small things. It might be difficult to pass. I wonder if I can get my mouse pointer here. Just above the mouse pointer, you will see at the end of a sort of short rod, that is actually the head of a spider that we decided to scan one Halloween. And it was already dead when we found it. Why does nobody ever believe me? Well, we found it, somebody else found it. It was underneath a piece of equipment downstairs. I'm making it worse, aren't I? Anyway, in this setup, the sample is on a nice little rotation stage where it will slowly rotate, and then you can see this sort of diesel engine looking thing on the left is our X-ray source, and you can just see peeping out on the right hand side what looks like a television, but it's actually one of our detectors, and then behind that is actually a series of lenses for us to zoom and magnify. Yes, we can do some zoom and magnify, very science. So this is one example of our scanners in the lab. Here's another example. We have a series of walk-in bay style scanners for when you do need a bit more space and you're scanning something a bit bigger. So here is I believe he was a PhD student. So here is a PhD student for scale. And what a great job he does. And you can see it's the same geometry again. We've got an X-ray source, the big silver thing on the left. Ooh, back. In the middle is the rotation stage on a heavy duty arm. And then on the right, this big old TV screen looking thing is actually our camera, our X-ray detector. So we're able to scan things from the pretty big to the very tiny, and all things in between. But how does it work? So here is, oh, Have we lost it? Hang on. Good, I'll take a drink. That's fine.
Yeah.
Oh. Right. Are we back? Mm. Oh, fantastic. Right. Right. So it struck me the other day that if I wanted an example of something where I was describing slices, I needed something that I could easily disassemble into slices. So I thought, oh, I know, a pack of playing cards. And that's what currently is rotating very, very slowly on the screen, is this very pack of playing cards in the X-ray scanner. So it's a bit it takes a moment to get your eye in, but you can see that it is indeed slowly rotating. And that's important because the more X-ray images we take, the higher resolution our data can be. It's a bit more complicated than that, but let's just go with that. And also you can see how we've got a nice grayscale contrast between our backgrounds and our deck of cards, which has a nice sort of grey. And you can even see when the angle is just right, you're actually able to see the individual cards in the deck. I'm not going to let this play. This video took me ages to put together. All my software was just having none of it. It's like it didn't want me to do this talk, but I shall not be defeated by the likes of technology. Right, so we've got our X-rays of a deck of cards, and what we're going to do, well, the way that it works, I should say, is, for example, let's take the middle of the deck, the Ace of Spades. And what we're going to do is simply look at that single slice of data. Now, back in the raw radiographs that we saw, the deck of cards rotating around, we're no longer thinking about that entire image. Instead, what we're thinking about is a single row of pixels right in the middle of the image. So it stops really looking like a picture and starts just looking like grayscale that sort of changes intensity and variation. But that's how this works. That's what the computer takes as its first data point, that single line of data that's changing as it rotates, and we're able to create a reconstruction, that's the word, of our deck of cards. So something I handed out earlier, and I've got a few more copies if somebody else would like a go, is I find that the best way to sort of properly understand what the computer is doing when it does tomography is to actually try and do it yourself. So I made a little tomography puzzle for you. This is a very popular, okay, it's a known puzzle game. I like it, it's a fun game. Right, anyway, the point is you have a grid of blank squares, and you're told along the sides and along the top that there are a series of coloured boxes with gaps between it. It's a bit like battleships in reverse, where you've got to colour in and you make a picture. So I'll maybe let you have a go for a minute. This is really sneaky because it means I can have a drink again. But I'll let you have a look. I won't bore you by making you complete the puzzle, but in a few minutes, just have a look at it, have a sort of appreciation, and then I'll bring it back and actually explain what this has to do with the rest of the talk. So yeah, if anybody needs a spare copy, I'll hand it out, and I'll also wander around so you can accost me with questions. Right, has everybody who wanted to have a go had a go? Don't have to have finished it to have got the. I'm going to show the results, but you probably won't remember them, so you can finish off the puzzle later. So here's the grid that you were presented with, and the astute among us quickly worked out that some rows nicely already add up to 16 along, so you can automatically fill them in, or 8 down, so you could automatically fill them in, and then you started to build up logically from there. And this is essentially a logic puzzle, but it is actually a form of tomography. It's called discrete tomography. And the reason why it's called discrete is because you're already told in what little packets you get the information in. So this is what this ends up looking like, depending on how you're feeling today with this Rorschach test. This is either a bird carrying some branches, or a weird looking dragon spitting fire, or anything else you might fancy to look at. And believe me, I had to actually try this puzzle a couple of times myself when I made it, to make sure that it was solvable uniquely, because although discrete tomography should have a unique solution, what if I was to give you the tomography like this? Instead of giving it to you in discrete packets of information, I just gave you the total of each row and each column, and said, well, there you go, all the information you need, off you pop, chop chop. And this is actually what the computer gets when we give them that row of pixels from the X-ray image. Bit more tricky now, isn't it? So the question is as well, how would we start solving this linear tomography, as it's known, where you have just a sum total of each row and column? You know, do we need anything else? What can we do? And the answer is that in the state that it is now, where all we have is rows and columns, there is not a unique solution to this puzzle. Because, for example, this row that has 10 on it, well, that could be 10 all grouped together. That could be 10 where it's 1 and then a gap, and then the rest of the row is 9 up until the end. We just don't know. And so for the computer, what the computer needs is what we actually give it, which is lots of different angles. We don't just give it an angle of basically 0 and 90. We give it 0 and 45 and every other angle in between, all the way around 360. And that's why we have to take an X-ray image all the way around the object, so that the computer actually has enough information to create a unique solution. If it was already handed the information nice and discreetly, it would need very few angles at all. In fact, it would just need what we get with the nonogram puzzle. It would just need 0 and 90, and it would be away. So I apologize that this is a bit stuttery, but this is what the computer came out with after it had scanned my deck of cards, and each of these slices that it's slowly juttering through, because this is quite a large video file, I should have compressed it, is a single slice. And each of these slices was reconstructed separately by the computer before it moved on to the next row of pixels and reconstructed the next slice. So we started out with our deck of cards, we deconstructed it into individual layers, and then we came out the other side with a reconstructed deck of cards in the computer, ready to do what we'd like with it. And the question is, well, why would I want to have a digital deck of cards? I don't know, maybe, might be interesting. But really, usually we're scanning something far more interesting than decks of cards. And one of the fun things actually about the things that you scan and then look at in slices is you start to look at things very differently. So here's actually something quite familiar, hopefully, to somebody who's walked through the English countryside. But in this view, it takes on a sort of mysterious property. What are we actually looking at? Sort of looks like birds, or, well, does anybody want to have a guess what this actually is as we're going through slice by slice? I'll give a hint. Oh, someone said leaves. Give the man a medal. It's a branch of holly. And actually, if I just knit back, you can actually start to see that the bright white circle on the left-hand side suddenly in our brains becomes the central stem. And then those seagull-shaped things are actually the leaves as we're going through in cross-section. So I scanned this years ago for a Christmas project that we ran in my previous lab. And I still like the data. I think it's great fun. So with that in mind, I'd like to now explore some of the natural world with you, some that you'd consider more natural than others, because I'd like to firstly start with some archaeology. And archaeology is, well, they make excellent use of CT because years ago, we lost a huge amount of data by unwrapping mummies. People didn't know any better. They didn't realize that the wrappings could contain information, but we found out that actually, yes, they do. And also, we'd rather keep these precious artifacts, which were once people, intact. And so we wish to study them in different ways. So this is a rather adorable mummified package from the Manchester Museum on Oxford Road. And you can see it's in two halves. You have this sort of longer half, and I've kind of spoilt the mystery by, you can see a sort of skeleton peeking out. But on top, there's a second package. And what the museum curators actually wanted to know was, is there something in that second package? And also, what animal is inside the main package? Because it kind of looks like the animal has a backpack and it's carrying something with it into the afterlife. So is it carrying grain? Is it carrying its young? What's it carrying into the afterlife? So did a scan, and here's what we found. So nice little bit of animation, because when you have 3D data, you've got to make it look a bit zhuzh. So here we are, removing the outer wrapping, and we're revealing a skeleton of a rodent. I did a bit of research myself. I didn't scan this myself, but I've been analysing the data. And from what I can tell, it's probably a type of shrew, a large type of shrew, but a type of shrew. And regrettably, we found that actually inside the backpack, it's just wrapping. There's nothing inside there. To be honest, this is to be expected, because the Egyptian mummy trade, they were terrible. They used to cheat their clients by giving them mummified wrappings, well, mummified objects that they would use for sacrifice. And sometimes the mummifying tradesmen wouldn't actually include an animal in the wrapping at all, or then maybe include a bone. So there was actually fake mummies even during ancient Egypt. So, but here's one from back at my previous institution, credit to Swansea University. And in this one is a very nondescript package. Often you find mummified packages will sort of have a shape that suggests the interior. So a cat mummy will look like a cat. A bird mummy will sort of have a bird shape to it. But this was just a blob. But inside, is this rather gorgeous, very long, very slender snake. And isn't he or she absolutely gorgeous? And also, strangely, looking like it's biting its own tail. But yes, so without X-ray CT, we would never have known, because no one would ever have dared, in this day and age, open up these mummified packages, see what's inside. So now I have to remind myself what's next. Yes. So from archaeology to paleontology. There we go. It'll take a moment for this to get started. This scale bar, in case you're interested, at the bottom, it says 1,500 microns. That's 1.5 millimeters to people who speak normal. And what we're actually looking at here is we're going through slice by slice through the tooth of a megalodon. So a giant shark. You can see we're now zooming in on the dentine, and we can see this incredible serrated tooth. Very nice. And what I quite like is the fact that actually at the moment, one of my colleagues is doing research on human teeth at the moment. So we're looking at them in really high resolution, really, really small, so we can see all the dentine tubules. And what's kind of exciting is the fact that turns out teeth have been around for a really long time in the structure that they are today. So now it's picking out some of the interior structures, so some of the nerves, and then some of the I'm not a dentist, I don't know the bits. But anyway, you can see it's now picked out the interior structure in 3D. So it'll be the nerves and the various tubules inside this megalodon tooth. And just for a final flourish, the tooth in 3D, which I think is rather neat. So this has revealed something that perhaps could have been achieved if we'd destroyed the tooth. In a lot of scientific fields, there's a concept called serial sectioning. It's where you basically sand off a layer of an object, take a picture of it, sand off the next layer, take a picture, and back and forth until you have a pile of pictures on one side and a pile of dust on the other. But in this case, instead, we still have our megalodon tooth, and we have our data digitally, which we can look at in lots of different ways, lots of different angles. It's digital, we can manipulate it just how we manipulate photographs. So, moving on, warning. I had to include a spider because we had a lot of spider data, but this one is particularly exciting because this was a spider that was preserved inside Baltic amber. So for the arachnophobes, I would say that the size of this spider is tiny. It was basically smaller than the head of a pin. And so this is what it looks like in the amber. And then this is what it looks like when we take a radiograph. And this is the 3D reconstruction. So actually the spider itself wasn't really preserved. All we had was just an interior cavity that we were then picking up by detecting the difference between the contrast of the air inside the cavity and the amber on the outside. And you can see, well, it is rather beautiful. And we've even actually got, in some places, there was still some internal structure remaining. So we didn't just get a surface cast of the spider, we actually got part of the pedipalp, which is the bit of the spider that they use, well, it's the bit with the venom. It's the bit that we're actually afraid of when it comes to spiders. So, and of course, again, if we'd serial sectioned that amber, a lot of this data would have been lost. We wouldn't have actually known about some of the intricacies that we ended up finding in the data afterwards. Often you'll CT scan an object and discover more than you looked for in the first place. So, oh, next page, please. Thank you. So here's something still in the, oh no, something completely different. So this is a piece of moon rock. We've been very lucky in our lab to twice have moon rock specimens come in. And as you can imagine, they're some of the most valuable lumps of rock on the Earth. And again, we don't want to destroy it, we don't want to damage it, but we also want to image it in the highest resolution possible. So you might think it's a bit odd, the fact that it appears to be surrounded by ball bearings. But the reason for that is actually to help with the CT scanning, because the more cylindrical an object is, the better it scans. So the moon rock itself was packed inside a cylinder, the hollow spaces was packed with ball bearings, and as a result, it produces a much cleaner image, so we can get a feel for all the different mineral phases that are inside this lovely moon rock. And although the grayscale of an X-ray doesn't give you chemistry, you can infer things like the mineral of a rock. As well as a geologist, I've learned how to infer the mineralogy of a rock by looking at the shape of it, by looking at its density in comparison to its neighbours, all various other things, and then also by studying the rock itself and going, oh, there's a mineral on the surface there, it looks like this, I can see it on the CT scan, therefore I can infer that these other ones around the other side of the rock are the same mineral, probably. And so you can start to build up a 3D picture of the relationship between the minerals, and therefore you learn about how that rock formed and will tell us about, in this case, a little bit about the geological history of the moon. And that's pretty cool. I like that.
Was it made by melting or compaction or that sort of thing? What are you trying to find?
Oh, so this one, let me have a quick look. It looks like it's made out of fragments. So that suggests that it might be, yes, as the gentleman back there just said, sedimentary. So in the case of the moon, that probably means it was hit by a meteorite and then it all came back down again and compacted. So it's going to tell you about the history of the moon by depending on the sort of rocks that they have. So yeah, there might be primary rocks that were formed first when the moon coalesced, or you might have something that might be the product of, well, the nearest thing that the moon has to weathering, which would be meteorite impacts, creating dust, which then falls back. So from the distant space to the back garden, here is the garden ant. You'll probably never look at a garden ant the same again when you see those mandibles, but the little box underneath is 1 millimeter cubed, the scale. And I did a little bit of research on ants a while back, basically as an act of revenge. I was living in a flat when I first moved to Manchester, and I was afflicted by the 12 plagues of Egypt. And and one of them included ants, but not just any ants, not these lovely garden ants, which I don't mind in the slightest. No, plague ants, Pharaoh's ants, which most people have never heard of. And so they're worth having a look at. And this is another great thing that CT can do, is it can give us the ability to do a comparable study. We can take a 3D rendering of a garden ant to scale in the computer, a 3D rendering of this species of ants, the Pharaoh's ants, and compare them together, compare, contrast, in the same way that you would do with physical specimens, except on this scale, it's very difficult to do that. If you have something like a bird or a medium-sized mammal, you can get the tape measure out and do some quite nice measurements and compare that way. But when you're dealing with something so small, it becomes very difficult to do it under a microscope. And so something like CT really helps. So if we, next page. And then, because I was feeling fancy, I did a high resolution scan of the head of the Pharaoh's ants. And this actually helped me to positively ID the ant because I didn't have a powerful enough hand lens, and I was going to do this scanning anyway for my revenge. But I thought, well, this texture of the skin, this is really interesting. And I checked in the literature and found people who studied ants and discovered, yes, indeed, this texture of the skin is particularly typical of the Pharaoh's ants. And so I had correctly ID'd the little blighters. It was funny when I had pest controllers coming in and they were telling me all about Pharaoh's ants, and I'm there sagely nodding, saying, yes, this summer I have become the local specialist on this flipping ant. Yes, yes. All of the Pharaoh's ant specimens are indeed from my flat. I killed them humanely. I will confess to killing those ones. I won't tell you where they usually hang out. If somebody wants to ask me individually, I'll tell you later, but I'll spare you. So now to the seashore. And I love this one. So the sand dollar. It's a relative of the sea urchin, and it has a rather exciting symmetry and a rather exciting interior. So this was scanned by a colleague who was looking at nature as a form of bio-inspiration for engineering. So you could see that it had that interesting open work that sort of looked like struts and beams. And so she was interested in, well, is this sort of structure particularly useful that we can then apply it to real engineering problems? Is it just useful at the scale of a sand dollar on the beach, or can we extrapolate that out and use it for our own inventions? Because, hey, nature's had all these millions of years of evolution to come up with a good idea. Why reinvent the wheel? Let's just nick it. It's a bit more complicated than that. Obviously, she wrote a whole thesis, and it was more than just let's plagiarize nature. Now, I've mentioned about insects a few times. Insects are interesting for the researcher because they're one of the few things that a scientist can experiment on with impunity. You don't need to fill out ethics forms. Nobody really cares about them. It's all a bit sad, really. Basically, it's because people don't think that they have the same nervous system and can't feel pain the same as mammals or fish or birds or all of that. So, but the other strange thing about insects is they're extremely X-ray tolerant, such as this little dude, which is a maggot. And you can actually see what we're looking at is it's moving. It's being blasted by X-rays, and it's still alive, which is ridiculous. And if I could have found it, I would have showed you a different data set, which is that a colleague of mine worked on looking at butterfly chrysalis. watching them develop from initial stage where they'd just become the chrysalis after being a caterpillar, all the way up to the point where it was about to pupate into a butterfly. And one of the crazy things about that was the same chrysalis was scanned on multiple days, multiple times, survived the X-ray process. It was in the X-ray for a good few hours each time, and still continued to grow and develop. It eventually didn't survive. I think probably because it didn't enjoy being manhandled as much as being in the X-rays. But it's incredible that we were able to do essentially a time-lapse study with a live specimen. It's the only thing we will let people put alive into our scanners, nothing else. Yes, sir. Yes, the question being, is there a chance I will be bitten by a radioactive spider in the lab such that has been irradiated by our lab machines? And the answer is, if it happens, I'm hoping for Spider-Man powers and not for Green Goblin powers, where I go a bit insane. But let's actually have a look at what this maggot looks like in 3D. Turns out maggots are basically just digestive systems. Who knew? Makes sense though. That's their job. Their job is to eat and eat and eat and eventually pupate and become a fly. So here's us flying sort of into the void, Star Trek styley, inside the digestive tract of this maggot. I'm not sure who made this video. It wasn't me, but I'm curious as to why they went for bright blue and bright red as the color scheme, possibly to distract from the fact that it's a maggot. But as you can see, it's a very nicely detailed maggot. But again, maggots are used and other similar insects are used as proxies for all sorts of things to do with human medicine. I knew a researcher who was looking at a particular caterpillar from the Galeria family of moths, and she basically infected them with Crohn's disease because she wanted to then cure them of Crohn's disease. And so we were CT scanning these moth digestive systems to see how those drugs were taking effect, because they were a good proxy for the human digestive system. So poor insects, but potentially excellent news for people who suffer with things like Crohn's. So I'm giving you this extra information to prove that we're not just doing this for fun. Like, there's science happening, honest. Right, hang on. Oh, what's this one? What's this one? I can't remember. Oh yeah, haha. Right. So sometimes though, idle curiosity gets the best of you. And I was out walking one time on sand dunes near the university in Swansea, and I happened upon an owl pellet. And frankly, I was delighted because I've always wanted to find an owl pellet. I think it's fascinating. And then I thought, well, the next thing after finding an owl pellet is scanning an owl pellet. So that's exactly what I was able to do. And a lot of naturalists will find owl pellets and dissect them with tweezers and a dish of water and see what's inside. But I thought, well, maybe we're losing some information if we just pick it apart. What if we see the shape of it? Does that tell us something about actually how the owl gets rid of that waste from themselves, shall we say? And you can see actually it's quite elongated. It was quite elongated. I'll play the video again. Oh no, that's a maggot. It's fairly elongated, like the long bones all sort of line up, and that probably implies that as it throws it back up again, it probably elongates. But also I could see lots of different bones in there, and I didn't have to get my hands dirty. There's at least 2 rodent skulls in there. There's a tail of some sort of rodent, lots of lovely long bones, and that I've highlighted in blue here are the densest regions. And then there was also all the fur wrapped around the outside. So I will admit that was a bit of idle curiosity, but also some delightful bits of sort of naturalist study. But thank you for bearing with me. I'm now going to indulge myself by talking about something that was part of my PhD work. So this is a sediment core from the North Sea. About 6,000 years BC, there was a huge tsunami-inducing landslide called the Storegga landslide. And it produced a massive tidal wave, obviously, tsunami, that inundated the Norwegian coast, a lot of Scotland and the islands, etc., all the way down. And it left a deposit of sediment, really thick, huge, meters and meters of sediment. But I was interested in a layer of sediment just below the landslide. I was interested in the fact that just prior to the landslide, there had been a volcanic eruption. And I wanted to look at that deposit of volcanic ash. So what we have here is one of my samples. The areas that are in bright red are volcanic ash. And the green, blues, and yellows are the sediment. It's sort of a muddy, sandy sediment. And false colour, obviously, the real sediment is not this brightly coloured, it's grey. But what I was able to find is the worm burrows of some creatures that were digging around in that mud over, well, what would that be? 8,000 years ago. 8,000 years ago, worm burrows, which is, I think, is pretty exciting. And it told me a lot about actually what was going on just before this massive landslide, and told me a bit more about my what I was looking at in terms of my PhD data, which I shall no longer bore you. But last and by no means least, I told you about my colleague who was looking at bio-inspiration. And sometimes you find bio-inspiration in the most unusual places. And for me, this unusual place would actually be the seashore or a bird cage, because the next specimen is a very small piece of cuttlefish bone. Cuttlefish bone, if you've ever seen it, they're actually quite light. And the reason for that is they have a very open labyrinth-shaped structure. But it's not just a labyrinth-shaped structure, it has layers. It looks like, well, in cross-section, it looks like the side of a building. You have floors and you have rooms. And well, I'm spoiling it, so let's just have a look at the video. So we'll get in a bit closer in a second. So already you can see that it has this incredible labyrinth structure in between layers, and it is literally like floors and rooms. And the question is, well, why does it have this labyrinth structure? And the argument seemed to be from her experiments that she did, including some mechanical testing, is that it contributes to the strength. And the way that the cuttlebone actually fails when you put it under compression is a bit like actually how a building fails during an earthquake. So you will get pancaking, where one floor will fail, and then another floor will fail, and then another floor will fail, and then another, all the way down. But of course, this also must be contributing to the cuttlefish's ability to be buoyant, because they float at a particular level in the water. And I'm still astounded by just how intricate and complicated and beautiful something as simple as cuttlefish bone actually is. But and I thought I would finish with this one because it's not something I scanned. I've got no ego in this, but I really do think that it's fascinating and beautiful and really shows the power of X-ray CT. This is something that we couldn't have seen with any other technique. Cuttlefish bone is so fragile. If you try and serial section it, it just disintegrates. You don't see the layers. You can't really see this structure just in 2D under a microscope or with a hand lens. It's only in the 3D that we get this structure and we get this revealed to us using X-ray CT. So thank you very much for your time this evening, and I hope that has been interesting.